Welcome to the course on computer design of electrical machines. We'll have a lecture 21 today on design of three-phase synchronous machine part 3. For as a outline of the presentation for today, we'll like to talk about design of synchronous machine, history design of silent pole machine, continue which we are already covering, and then design of cylindrical machine for turbogenerator, then numerical questions and references. So coming to design of this synchronous machine, starting from silent pole machine as we were discussing with the design of field winding. As you can see how the field winding plays between the on typically pole body. As you can see, portion of hair of field coil with the strip on edge conductor. So typically wire wound coils are generally for machine with a small number of poles, and the field coil of a small alternator having a large number of poles are wound with the glass covered rectangular strip, and field coils of large slow speed alternators use strips on edge winding where the bare copper strips are insulated from each other by interturn insulation. So with the class B insulation, internal insulation in 2 layers of asbestos paper and 0.18 millimeter each, and class F insulation, intertube insulation of 3 layers of asbestos paper and with the 0.18 millimeter each, and pole body insulation is epoxy glass laminates and is 4 millimeter thick. The coil is consolidated under the pressure of 4 to 12 mm meter square like. So as a photograph, you can see how look like a typically the field coils of the large silent pole synchronous machine as a silent pole structure with the field winding. As you can see in the diagram as well as the photograph of that same. So coming to typically for the design, as you can see here with the for the calculation of the length of the mean turn, considering the current density of delta F of the field winding is assumed to be between 3 to 4 millimeter square. So field winding is represented as in figure. So total copper area of field winding is 80 F by delta F, and that is 2 ATA upon delta F. Assuming the suitable space factor delta F, the total winding space is estimated as total space for winding equal to total copper area in the field winding delta divided by sigma F. So total space for winding, that total copper area divided by delta F, and the height of the field winding HF equal to total winding space divided depth of the field winding DF, and length of mean turn of LMT of field winding, LMT equal to 2 LM plus pi in bracket BP plus 0.01 plus DF, and where the LM is the LM equal to 0.9 L and BP is the width of the field winding and DF is the depth of the field winding. So the field MF required by the machine on the full load had to be estimated. Since the dimension of magnetic circuit is not yet known, an approximate estimation can be done as follows. So field MF, we already considered that ATF equal to ATA into SCR, and where ATA is equal to 2.7 I PH and TPH into KW upon P, and typically you can see the field coil structure how it should look like for the silent pole machine. Now coming to typically procedure for designing the field winding. In order to design the field winding, the exciter voltage must be known. The exciter voltage varies between 50 volt to 400 volt of different rating and types of the machine. So this is specified by the customer, and a voltage of 125 volt is used for small and medium size machines, while the exciter voltage of 250 volt is used for large machines. The field winding should be designed for a voltage from 15% to 20% less than the exciter voltage to allow the drop in voltage between the field and the exciter to allow variation in reluctance of magnetic circuit. So voltage across the field coil VF or EF equal to VF equal to 0.8 to 0.85 of V divided by P, where V is the exciter voltage. Now coming to, we know HPL, the height of the pole, from which we subtract the height of the shoe H1 and also thickness of pole, flange, etc., and the space left in the winding height HF. So HF equal to HPL minus H1 minus space taken by the spool flange, etc. So space taken by the spool flange is approximately 20 millimeter, as you can see in the figure. Now suitable depth of the field winding DF is assumed, and the mean length of the turn is evaluated. And the following tables used normally as a reference. Depending on the pole pitch starting from 0.1 to 0.4, the winding depth DF in millimeter usually varies from 25 to 45 millimeter. So now coming to voltage across each field coil, EF equal to field current into resistance of the field coil at 75 degrees Celsius, and EF equal to IF RF equal to IF TF into rho LMT upon AF, where TF is the number of turns in each field coil and IF RF is the field MF per pole at NF and IF is the field coil at pole, that is ATF, and AF equal to ATFL into rho LMT upon AF, or the area of field conductor AF equal to your ATFL rho LMT upon AF. So now the value of the field current can be calculated by assuming the suitable value of the current density in the field conductor, and current density in the field conductor can be taken as a variable for iterative design, and current density delta F or the field winding is assumed between the 3 to 4 ampere per meter square. Therefore, field current equal to current density into area of conductor, that is your delta F into AF. Now, number of field turns, that TF equal to ATFL upon IF, and since the number of turns is a whole number, the current density may have to be readjusted in case of mixed number is obtained. We know the winding space, and then we can easily find out whether it is possible to accommodate the field turns or not. In case the winding space available is less, increase the depth, and if space is more, decrease the depth until the winding fits in it. So now the resistance of the field winding at 75 degrees Celsius, RF equal to rho LMT TF upon AF, and the copper loss at field winding at 75 degrees Celsius, QF equal to IF square RF or IF square TF into rho LMT upon AF, and this loss is to be dissipated by the field, and therefore we must check that the temperature rise is within the limits. Now coming to temperature rise calculation of the field winding. So dissipating surface of the field coil is S equal to 2 LMT in bracket HF plus DF, and hot spot temperature rise of the winding above the ambient, that is delta W equal to delta instance plus delta S plus delta E, where the instance is temperature gradient across the slot insulation, delta S is temperature rise of cooling surface above that of the cooling medium, and delta C is the temperature rise of cooling medium over the ambient temperature. So now steady state temperature rise theta S equal to QC upon S, where or theta S equal to copper loss into CF divided by S degree Celsius. So important is because by keeping the surface temperature, the winding temperature of the winding cool, the internal resistance of the winding are also kept low. So now typically here you can look surface temperature rise for calculation. The cooling coefficient C decided from the given table. So here is given for different kind of the surfaces. So if you look into the typically rotating field coils, it varies 0.08 to 0.12 divided by 1.0.1, and typically your 0.6 to 0.8 divided by your 1.01 depends on the armature periphery and based on the total solar surface or exposed to this like So of course this is the table for cooling coefficient for where V is the peripheral velocity. Now the problem of calculation of temperature rise of the field coils is complicated by the fact that the fanning action of the rotor has an important effect on the capability of machine to dissipate it. It is therefore clear that the heat dissipated from the surfaces of field coil depend upon the type of construction of the machine, nature and area of the surface, and heat absorbing property of the surrounding medium. So therefore, the predeterminants of the temperature rise of the field coil is based upon the empirical coefficient derived from the experience and experimental investigations. Now, surface temperature rise calculation. The loss dissipated from the surface of field coils are only the copper losses in winding, and there are no iron loss in the core of the field coils of the DC and the synchronous machine, as they are subjected to varying non-varying magnetization. So the calculation of temperature rise is based upon the total coil surface. So considering the figure S equal to 2 LMT DF plus 2 LMT HF, that is equal to 2 LMT in bracket DF plus HF, and this S equal to 2 from the dimension of the field coils, as you can see in the figure, that comes 2 in bracket BP plus DF plus LP plus DF, and that is equal to 2 in bracket LP plus BP plus 4 DF, where DF is the rail depth, H is the axial height, LP is the length of pole core, and BP is the width of the pole core. Now some surface temperature rise calculation, cooling coefficient to rotating field coil CF equal to 0.08 to 0.12 divided by 1.0.1 VA, where VA is the peripheral speed and suitable value of is taken for the CF. So therefore, temperature rise steady state temperature rise theta is equal to QC QF into CF divided by S. So temperature rise of the coils should be within the specified limit. If it exceeds the limit, increase the depth of the winding, and this increases the current density in the winding and thus reduces the copper losses. So final check applied is to note the clearance between the adjacent field coils from the pole drawing and the minimum clearance that should be about 15 millimeter. And this is the flow chart for typically for rotor design. With the start, then input design data. Assume the flux density in the pole area from 1.5 to 1.7 Tesla and leakage factor of 1.15 to 1.2. Then calculate the pole area of the pole AP, usual flux per pole area into leakage flux Vy and AP, and then AP by this AP gross equal to AP upon stacking factor. Then the fix of the shape of the coil, whether circular or rectangular. If it is a circular, width of the pole WP equal to 4 upon pi AP and P equal to L. And if it is a rectangular, then width of the pole WP equal to your AP divided by LP and LP equal to L, and then output WP, LP and AP for final dimension of the typically the field structure. And this is typically the complete design flow chart of the field winding. So you have to typically start, then input the design data, then is the exciter voltage is specified, yes, then calculate the voltage across the each coil, VR equal to 0.8 to 0.85 and V by P. And well, if it is not known, then you assume the exciter voltage as 125 volt for small machine and 250 for large machine, and go to HP in known, or assume the HP equal to HP1 equal to HP minus 20 millimeter, 20 millimeter for spool, and then go to HP as a known, assume HP equal to this minimum, then calculate the ATA 2.7 IPS TPH kW upon P and ATF equal to your AT A into SCR, taking current density sigma 3 to 4 ampere per meter. Find the total copper area of AF equal to AT upon sigma F and take the space for copper AF upon sigma, where the sigma F is the space factor. Assume the depth of the winding DF and calculate the length of the field winding LMT equal to 2L plus pi in bracket WP 0.01 plus TP and LM equal to 0.L, and then calculate the resistance of field winding RR equal to rho LMT TF upon AF, where the area of the field winding AF equal to ATF rho LMT upon EP, and then field current is your IF equal to sigma into AF, and number of field turns is PF equal to ATFL upon F. Then assume the field winding suitable in the space height HF and depth DF. If the winding space is less, then increase the DF, and if winding space is more, then decrease the DF, and repeat the process until the winding is suitably fit into the it, and then F equal to ATG upon 10 power loss into sigma F into DF under root of that if loss is known, and then calculate in loss in each field coil WF equal to IF square RF or IF square low LMT TP into 1 your AF, and then check the temperature rise S equal to cooling surface, that is 2 LMT as DF, and temperature theta equal to copper loss into CF into S, where CA if you are 0.04 to 0.16 divided by 1 plus 1 0.1. Check if your theta is less than specified value, maybe typical value rise 40 degree. No, then increase the DF. If yes, then stop. So now coming to in case of certain pole machine calculation of short circuit ratio. So SCR or short circuit ratio is the ratio of excitation required to induce the rated voltage on no load to the excitation required to calculate the rated current under the short circuit condition. So the speed for both cases being the rated speed. The SCR equal to MF for rated voltage at no load and MF for rated current at short circuit. So SCR can be calculated from the open circuit and short circuit characteristic of the synchronous machine. So typically here you can just see how open circuit characteristic and short circuit are shown here, and from this you can find out typically your SCR equal to OD upon OE, and equal to CD upon B or CD upon AD, or SCR equal to 1 upon XS and or XS equal to AD upon CD is the synchronous reactance. So now on short circuit, the field MF is mainly used to overcome the armature reaction or armature MF. So no load MF upon pole equal to SCR into AT upon pole. So since AT per pole is the measure of the armature reaction, so SCR give an indication of the distortion and demagnetization of main field due to the load current, and higher value of SCR indicate minimum changes in the field current to maintain the rated voltage under varying load conditions. So now the machine with lower value of short circuit ratio will have higher synchronous reactance and poor voltage regulation, then poor stability as the stability is less synchronizing power, less short circuit current and lower length of wear gap. And the typical value of SCR is for turbogenerator is 0.5 to 0.8, hydrogenerator is 0.9 to 1 per unit, and synchronous condenser is short of 0.4 SCR value typically. So now coming to design of damper winding for 7-pole machine. So damper windings are low resistance copper or aluminum bars placed in slots in the pole faces of a synchronous machine, and these bars are short circuited on the either side by the ending similar to the squirrel cage induction motor, and the design of damper winding depends on their purpose. In synchronous generator, it is provided to suppress the negative sequence field and to damp the oscillation when the machine starts hunting. And in synchronous motor, the function of the damper winding is to provide the starting torque and the damp the oscillation while hunting. So the damper winding placed in the pole as shown in the figure, how it should look like. And the design of damper winding of synchronous generator is to suppress the inverse rotating field is discussed here. The amplitude of fundamental MMF of any phase of the pole polyphase winding is given AT1 equal to 4.5 ATM cos omega t n equal to 0 to infinity kWn sin nx upon n, and keeping a value of n equal to 0 at t equal to 0 and x equal to pi by 2 for one phase. AT1 is 4 by pi ATM into kW, where ATM is the amplitude of the phase m at t equal to 0, and this ATM equal to maximum conductor current into number of turns per pole per phase, that is equal to root 2 IS into slot per pole per phase into conductor per slot by 2, or equal to root 2 IS Q ZS by 2 or Q ZS IS divided by root 2, where Q is the slot per pole per phase and that is the conductor per slot, that is 2 TPH upon 2P, and IS is the RMS value of the current in each conductor, that is IS equal to IPH. So AT1 is equal to 4 into root 2 upon pi IPH TPH KW1 divided by P, and this pulsating AT1 is resolved into two rotating field, namely synchronous MF and the inverse MF, each having half of the magnitude. So damper winding is to be employed to suppress the inverse field. Therefore, the MF of damper winding must be equal to the MF of reverse field. So MF of damper winding equal to 4 into root 2 by pi IPH TPH KW1 by P, and ampere conductor per pole is now AC top P equal to CPA 6 IPH TPH by P, or MF for damper winding is 4 into root 2 by 2 upon pi AC into top P divided by 6 into kW, and this typically substituting kW1 equal to 0.955 in this equation. So we get equal to 2 root 2 upon pi AC top P by 6 into 0.995, that it becomes 0.143 AC into top P. So let the AD is the total area of damper bars per pole, and delta D is the current density the damper bars, and can be taken as 3 ampere to 4 ampere per millimeter square. So AD delta D equal to 0.143 AC into top E, and from this we get AD equal to 0.143 AC top E divided by delta D. So total area AD for the damper winding is distributed into a smaller cross section depending upon the number of bars used. So AD equal to 0.143 AC top E divided by delta D, and the slot pitch of the damper is made different from the stator slot pitch by about 20%, and this is to reduce the current induced in the damper winding due to the tooth triple, and then pole arc equal to number of the bars per pole into the 0.8. So length of each damper bar LD equal to 1.1 L for a small machine and L plus 0.1 for larger machine. Area of cross section of each bar AD equal to total area per bars per pole divided by number of bars per pole, that is AD upon ND, and for circular bar AD equal to pi upon 4 into DD square, and area of end ring sorting the bar, that is A ring equal to 0.821 into AD. Now the process for designing of this as a flow chart of this, with the starting we put the input specification, then calculate the total area of the damper winding per pole, AD equal to 0.2 AC top E by your delta D, where T the tau is the pole pitch, and pitch for damper winding is 0.8 of Eustace slot pitch. The number of damper bars ND equal to pole arc upon diameter damper pitch, and area of the damper bar AD equal to your AD divided by number of bars, and diameter of each bar equal to D equal to 4 AD upon pi under root of that, and length of each bar LD equal to 1.1 L, and then you output AD, capital AD, small AD, and D, and DD and LD. Then stop. Now coming to calculation in solid pole machine, the magnetic circuit calculation. So the fundamental relation for magnetic circuit calculation are discussed here. The magnetic circuit for pair of poles for silent pole machine is shown here. As you can see, typically, I mean, how the flux is flowing in different parts, starting from pole rotor core to pole body, then pole shoe, then typically stator teeth, then stator core, and then again goes back to throw another pole. Like so, for the calculation of magnetic circuit, first, because the maximum MF required for air gap, so first we will consider air gap for MF calculation. So in case of silent pole machine, the length of air gap is not constant over the whole pole pitch. So this gives rise to different value of air gap flux density over the pole pitch. And MF required for air gap of silent pole machine, that we call denote by ATG, is a flux in a flux tube X, reluctance of the tube length, and the reluctance of flux tube at the center is equal to effective length of air gap at the center and mu0 into area of the flux tube at the center, and that is kg Lg upon mu0 into area. So it becomes ATG equal to BG into area of flux tube at the center. So it becomes 800,000 BG kg into Lg, where your kg is the gap contraction factor. And this value of the typically magnetization characteristic for other part of magnetic circuit, because we have a ferromagnetic material, usually use like a cold rolled granite or distill, typically like a grade 1 to 3, and how the characteristics are shown here for different flux density for required MF calculation. So from this these characteristics we have to take, that will go for every part of magnetic circuit from the flux density into this characteristic and get the per unit MF, that is 80 ampere per meter of the your magnetic circuit length, and then we multiplied the length of magnetic circuit, and that gives the total MF required for that particular part of the ferromagnetic material as a part of magnetic circuit. So this is typically you can call it BH curve or BH curve for dynamic steel. So different material are used. So that's why the characteristics are given here. Now coming to the MF for armature teeth, the parallel sided slots are used in synchronous machine, and therefore the teeth are tapered. The MF for teeth is found out by finding the flux density BT 1 by 3, and the length of flux path in the teeth is equal to the depth of the slot, that is ds, and BT 1 by 3 is the flux density 1/3 height from the narrow end, and 83 is the value of the MF per meter for BT 1 by 3 as associated by BAT characteristic, and the total MF required ATT is equal to 80 by 1 by 3 into LT, that is 80 1 by 3 into ds. So that gives the MF for the teeth. Like now, MF required for the core, the corresponding to the flux density BC, the MF per meter ATC for the core is found from the adjacent figure, and total MF for the core ATC is equal to small at into LC, where you can call it the length of flux path in the core is taken equal to 1/2 of the pole pitch over the mean diameter, or LC equal to pi in bracket capital D plus 2ds plus dc divided by 2p. Now coming to MF for poles, the flux in the pole equal to the usual flux that crosses the air gap and enters the armature plus the leakage flux, and actually the flux in the pole is not uniform throughout a radial length owing to different values of leakage flux from the pole shoe and pole body, and it is assumed for calculations that at the top 2/3 length of the poles carry the usual flux plus leakage flux between the poles. So while the bottom 1/3 length carries the usual flux plus the leakage flux from both pole 2 and pole body, and thus the flux at pole top is minimum while at the bottom it is maximum. So this MF for poles for both pole 2 and pole body. So minimum flux in pole is equal to phi p minimum equal to phi p plus phi SL, and the maximum flux in the pole is phi p max equal to phi plus phi SL plus phi PL. So leakage flux from pole 2 and the body is given as phi SL equal to 4 pi AT in bracket LS HS by CS plus 1.47 HS logarithmic 10 in bracket 1 plus pi BB pi BS divided by 2 CS, and where the pi PL equal to 2 mu0 ATL in bracket LP HP divided by CP plus 1.47 HP logarithmic 10 in bracket 1 plus pi BP divided by 2 CP bracket close. So axial length of the body is LP equal to axial length of the pole, so that is LS. So total MF ATL is equal to ATG plus ATT plus ATC, and from this it follows that maximum flux density in the pole body is BP equal to phi maximum divided by AP, and the minimum flux density in the pole body is phi P minimum equal to phi P minimum divided by AP. So MF for poles, the MF per meter corresponding to BP max and BP minimum are found from the figure BAT curve, and let them be at ATP maximum and ATP minimum. Therefore, the total MF for the body is ATP equal to ATP small ATP maximum into HPL divided by 3 plus ATP minimum 2 HPL divided by 3. So that gives the MF required the complete pole body. Now MF for the yoke, then MF in the yoke is y equal to phi plus phi PL plus phi SL by 2, and area of the yoke AY is equal to length of the yoke into depth of the yoke, that is L into dy. Therefore, flux density in the yoke is By equal to phi y divided by AY equal to phi plus phi PL plus phi SL divided by 2 Ly L dy. So corresponding to this flux density and the material of the yoke, the per meter ATY for the yoke is given from BAT curve depending upon the material used. Therefore, the MF for yoke, where Ly path for the magnetic flux through the yoke, which is taken 1/2 of the pole width on the mean diameter of the yoke, that is Ly equal to in bracket pi dr minus 2 HPL minus dy divided by 2p, and the total MF required at no load is F0 equal to ATG plus ATT plus ATC plus ATP plus ATY. That gives the 5 parts of the magnetic circuit to get total MF required at no load. Now coming to open circuit characteristic of the machine, open circuit characteristic give the relation between the terminal voltage and no load and the corresponding MF per pole, and also is shown in the figure. As you can see, the y-axis the open circuit voltage EG, we call it induced, and axis is the field MF like AT or typically ATN. So now getting a full load MF, the value of the full load MF ATFL can be calculated for the sequence. Select the suitable voltage scale and draw the, as you can see in the figure, draw the your voltage EPH equal to V and draw OI. As you can see here, armature current per phase at angle phi with respect to EPH, where cos phi is the power factor lagging in this case, draw AB. Typically, AB resistance drop in phase with the current after the V, that is IPH RAC parallel to the OI, and then draw BC leakage drop per phase IPH into XL and perpendicular to OI, and join OC, C from original OC, then OC is the generated voltage EG. Corresponding to this voltage EG, find the M from open circuit characteristic and let this to be AT gen, which is shown in AT gen here like or so. Now plot OD to some scale and then DE, field MF equivalent to armature MF per pole at full load perpendicular to OI at DE, and then field MF equivalent to MF per pole is 2.7 IPH TPH kW upon P into rho d, where rho d is alpha plus sine alpha divided by 4 sine alpha by 2, and the value of kr cross coefficient is obtained from graph on line DE cut off df equal to kr into DE. That D typically you can get kr typically from this characteristic which varies from polar to pole pitch ratio, and join OF and extend it, draw a perpendicular form E of OF extended cutting it at GI, and then OG is the full load MF ATFL from this phasor diagram. Of course, this can be correlated in terms of the typically in equation also, so that you can do repetitive calculation for the calculating total MF for different loading conditions. So now coming to self-balancing determinants of direct and quadrature axis reactances. The magnetizing reactance per phase of a cylindrical rotor machine with the uniform air gap with the three-phase winding is Xm equal to 7.54 FTPH square Kw square dl upon P square Lg into Kg into 10 power minus 6, and per unit magnetizing reactance Xm equal to IPH Xm divided by EPH. To obtain the armature reactance in direct and quadrature axis for cylindrical machine, this expression must be multiplied from flux distribution coefficient. So the per unit direct axis reactance is XAD equal to AD1 into Xm, and per unit this is where AD1 is the distribution coefficient for direct axis, that is your rho d into A1, and rho d is the reduction factor for direct axis armature MF equal to rho d equal to alpha plus sine alpha divided by 4 sine alpha by 2, and A1 is Bm upon Bg, that is alpha is the span of pole R, and now per unit quadrature armature reaction reactance is XAQ equal to AQ1 into Xm, where AQ1 is 4 psi plus 1 divided by pi minus sine psi pi divided by pi, that is flux distribution coefficient, and phi is the ratio of polar to pole pitch. So now per unit values of the unsaturated reactances of for the two axes are direct axis synchronous reactance XD equal to XL plus XAD, and quadrature axis reactance is X equal to XL plus XAQ, and phasor diagram based upon the two reaction theory for generator is shown here. So we start again from typically you can see the phasor diagram for typically from EQ, that is the voltage, and then we from the V, we start from V, and from V we plot a correct and with the as a phasor angle phi psi we draw the current, and from now with this current perpendicular to typically you can just see we draw the perpendicular to I, we draw I typically XL and IXD virtually you can see IXD, and from IXD now what we do it we cut typically value of from this the EQ, and passing from 0 to EQ the point that where it cuts it comes the quadrature axis, so we identify quadrature and direct axis, and now from based on that virtually we draw on the quadrature axis the value of IDIQ, IDXD, and perpendicular to that IQSQ. So that completes the complete phasor diagram here typically like. So now coming to phasor diagram, it depends on, so here for two reaction theory for generator it is shown here V, then IQ, that gives the virtually of E for cylindrical pole because XD equal to XQ, and reaction factor for direct axis here rho d is pi square psi divided by 8 psi pi by 2. So now the short circuit characteristic, the relationship between field MF and the armature current when the armature is short circuit are known as the short circuit characteristic, and the armature short circuit characteristic is proportional to field MF over the wind range, so that the HCC is a straight line. So if CD equals to, here in the graph, if CD equal to rated armature current I, then D is the point on the HCC for rated value of load OC equal to the field MF per pole to circulate the rated armature current under the short circuit. So you have a 1.4 rated and join the origin, and that will give the short circuit characteristic. Like you can have a both characteristic short circuit and open circuit characteristic from here. Now for the short circuit condition, the armature current is practically in quadrature with the voltage, and thus the armature MF has a demagnetizing effect on the field, and the voltage induced in the armature when the short circuit is nearly equal to IX equal to X and the leakage reactance top, and the field EMF required to generate this voltage is found from OCC equal to OOB. Well, the armature when short circuit has a demagnetizing effect upon the field, so field EMF equivalent to armature EMF is rho d into ATA, that is virtually shown, it is here as a BC. So now coming to the losses in cerebral machine, the various losses in synchronous machine can be classified as iron loss due to main field, iron loss due to parasitic field, I square loss in the armature winding, eddy current loss in the armature conductor, and straight load loss, and loss in the field winding, and friction windage loss. Now coming to iron loss, the iron loss is due to main field and the hysteresis and eddy current losses. The weight of the armature core and teeth are calculated as loss per kg and can be calculated from the equation your pi equal to ABM square watt per kg, specified in iron loss at 50 Hz. And here machine is AC, so you have a two-part core and teeth which are made, and this coefficient A is 4.7 and 6.5. So now coming to the pole phase losses, a ripple is superimposed on the flux density wave owing to the presence of slots in armature surface. So ripple move with respect to the pole and induces the eddy currents in the pole phases. The pole phase loss depends upon the slot opening, air gap length, number of slots, and the speed of the machine, and the poles should be laminated in order to reduce the pole phase loss. And in practice, either the poles are laminated or made of solid iron, the poles are laminated. And in turbogenerator, the rotor is solid, but owing to large air gap, the pole phase losses are small. So in synchronous machine, pole phase loss varies between 25 to 70% of the total iron loss. Now coming to copper losses, the copper losses represent I square loss per phase, that is IPH square RH, and total I square loss will be I3 IPH square RH. Now coming to the eddy current loss in conductor, the eddy current loss in the conductor is calculated with the total copper loss by introducing KE average, which is average eddy current loss factor by 4 slot portion of the conductor, and that is Ke equal to 1 plus alpha h to power 4 n square by 9, and total copper loss is 3 Ke IPH square RDC, where alpha is your typically 100 under root B WDS, where H dash is the height of strand and is the number of conductor layers in the slot. Now coming to straight load loss, the straight load loss occurs due to the stray field which appear when the machine is loaded. So for example, the armature EMF wave contains higher harmonics of the order of 5, 7, 11, 13, and these harmonics EMF cause higher harmonic field which travel over the pole phase and induced eddy currents there, and thus increases the iron loss at the load. Additional losses at load may be caused by armature leakage flux in the overhang region surrounding the iron portion and the end plate, and actually the stray field loss may appear in the pole phase, core and overhang and end plates. This loss is very difficult to calculate and yet may be comparable to with those of whole of the straight I square loss. So now coming to excitation loss, the field copper loss is equal to IF square into resistance of field winding. So beside I square loss, there is a brush contact losses on the slip ring. The following voltage drop may be assumed in brushes. So for carbon and graphite brushes, drop is 1 volt, and the for brush containing metal is a 0.3 volt. So if the pilot and the main exciter are driven from the same shaft, the losses in the exciter must be taken into account. Now coming to friction windage losses, so this loss consists of bearing friction and total windage loss. So this loss depends upon the type of construction, speed and rating of the machine, and varies between 0.2 to 0.8% of the kV rating, and the higher value are for the higher speed and high rating machine. While with hydrogen cooling, the total friction loss reduces to 0.3 to 0.4 of the kV rating. So now total loss equal to copper loss including eddy current plus straight loss plus iron losses plus friction loss plus excitation loss, and the rated power is kVA into power factor. So therefore efficiency at full load is rated out power divided by rated output power plus losses into 100. So now calculation for temperature rise. Now step 1 is cooling coefficient are taken from the table for a particular machine and the structure. I mean a cylindrical surface structure, so it's a cooling coefficient C is given depending on the peripheral speed, the different relation. So you can select the appropriate formula from different parts from this table. Now as a step 2, the cooling coefficient numerator has been selected, say as 0.03, Now the losses dissipated from each surface is calculated. Now the outer, for example, the outer cylindrical surface area is pi d0L, and loss is dissipated from back of stator core is in bracket pi d0L divided by cooling coefficient. And similarly, the loss dissipated for inner surface is pi dl, area of the inner and surface including duct, that is pi in bracket d0 square minus d square pi 4, and ducts are calculated, and the loss dissipated is the sum of all these losses. Now step 3, the total loss to be dissipated equal to copper loss in the slot portion of conductor plus iron loss, and therefore the temperature, every temperature rise is theta equal to total loss to be dissipated, like copper plus iron loss in watt divided by total loss dissipation in watt per Celsius, and the final temperature rise in Celsius. So the now coming to the voltage regulation. The voltage regulation can be found out by OCC curve. So OCC corresponding to full load MMF, the voltage at that E0 is taken as a per unit, and example E0 equal to 1.16 per unit, and regulation is 16%. Now this is typically you can see the photograph of like a turbo generator, large turbo generator, and for the calculation for design of turbo generator, or you can call it cylindrical machine, it has already been stated as a turbo generator is driven by steam turbine. Its diameter is limited to the peripheral speed. The maximum possible permissible peripheral speed is 180 meter per second, but it's limited normal as 120 meter per second. So thus the D can be calculated V equal to pi d ns, and for conventionally cooled machine B average is 0.55 and 2.65 Weber per meter square. AC is 50,000 to 100,000 ampere conductor. So specific loading used in large water cooled generator are B average 0.45 to 0.62 and AC is 180,000 to 200,000 ampere per meter. So now calculating for turbo generator the length of air gap. So length of air gap can be approximated by approximate value of the armature MF conductor per pole, that is AC into tau, and armature MF per pole AT equal to AC tau by 2 approximately, and no load MF is ATF0 equal to SCR into ATA, that is SCR into AC tau by 2. So short circuit ratio of the modern turbo generator is about 0.5 to 0.7. So assuming 80% of no load MF we lost in air gap, so MF required for air gap is 0.8 into SCR into AC into tau by 2. So but the MF required for air gap is 100,000 kg BGLG. From the education, the LG comes like 0.5 AC tau but by kg PG into 10 power minus 6, and taking a sinusoidal distribution of the flux density in the gap, B is equal to pi by 2 B average, and for the practical purpose B average BG is taken as 1.5 B average and kg is as 1.1. So number of slot per pole per phase is 8 to 9. So slot pitch may be 75 to 90 millimeter, and for modern water cooled turbo machines, the current density should be as high as 8 to 9 ampere per meter square, improved to 4 ampere per millimeter square for conventional cooled machine, and the slots are made deeper to increase the leakage reactance, and this is done to reduce the forces under short circuit condition, and this has the incidental advantage of spacing the overhang away from the rotor and ring, and 2 layer shorted winding is used, shorted by 1/6 pole width. Now coming to stator design of turbo generator, the single layer concentric or 2 layer short pitch windings may be used, and the advantage of single layer winding is that it can be easily clamped, but it gives a higher state load loss owing to overhang, and single layer winding can be shorted, and therefore flux harmonics have the full effect, and the stator conductor must be subdivided and transposed to reduce eddy current losses. Now coming to rotor design of turbo generator, the rotor winding is distributed in slots. The coil are of concentric nature with multi-turn type, as you can see in the typically in the diagram. So slot pitch is selected as so as to eliminate the undesirable harmonic, and current density in the rotor is 2.5 to 3 ampere per meter square for the conventional cooled machine and 10 to 12 for hydrogen cooled machine. So other design procedure and equation are similar to that of cylindrical synchronous machine, and typically you can see how typically the winding distribution and the photograph of the how the winding is put in the rotor of the typically in turbo generator. So full load MF can be taken twice of the armature MF. So full load MF by ATF will equal to ATA, that is 2 into 2.7 IPH TPH kW by P. Extended exciters may be taken. About 15 to 20% of this voltage is kept in reserve for excitation control. So for V to be exciter, is voltage for each coil is EF equal to 0.85 to 0.8 to 0.85 VE divided by P, and length of the mean turn of the winding approximately LMT equal to 2L plus 2.3 tau plus 0.24, where tau is the effective span of coils, and voltage across each coil is EF equal to IFRF, where the EF equal to IFRF equal to IF TP rho LMTF divided by F, or ATFL into rho LMTF divided by F, where F is ATFL rho LMTF divided by F, and where IF is field current, TFL is the number of turns in each field coil. So assuming a suitable current density delta F for the field winding, the total area of field conductor equal to 2P ATPL divided by delta F, and number of field conductor 2APF to ATFL divided by delta F into F, and conductor per slot is 2AP ATFL divided by D sigma F into F into SR, where SR is the number of wound slots in the rotor. Now coming to numerical problems. Calculate A, the size of armature wire, B, the AC resistance of each phase of 3-phase 50 Hz 8-pole star connector synchronous generator having a following data. So pole pitch equal to 0.3 meter, line current 100 ampere, slot per pole per phase is 3, conductor per slot is 6, and gross axial length is 0.3, length of active copper 50% of the total copper length, and average eddy current loss equal to 1.3, factor is 1.3, current density delta sigma equal to 40,000 by AC plus VA upon 16, where sigma is the current density ampere meter and AC is ampere conductor per meter, VS is the peripheral speed in meter per second. Now with the solution, armature diameter is D equal to 0.3 into 8 by pi, that is 0.765 meter, and synchronous speed NS is equal to 2 into 50 by 8, so that's 12.5 RPS, and peripheral speed BA is pi D, and it is 28.8 meter per second. Now the total number of slots is equal to 3 into 3 into 8, that's 72. Total number of conductors is Z equal to 72 into 6, 432, and turn per phase is 432 divided by 6 equal to 72, and current in each conductor is IS 100 ampere. All coils in connector in series. So small AC is IZ divided by pi D, putting a value it comes 18,000 ampere per meter, and current density in armature conductor sigma is 40,000 divided by 18,000 plus 28.8 by 16, so it comes 4.2 ampere per millimeter square. Now coming to area of the armature conductor, that is current divided by current density, so 400 by 4.2, that is 23.8 millimeter, and active length of each turn is 12 equal to 2 into 0.3, that's a 0.6 meter, and total length of the turn twice of the active length, so LMT equal to 2 into 0.6, that's 1.2 meter, and DC resistance of each phase at 75 degrees Celsius is RDC equal to 0.01 resistivity into 72 into 1 by 2, 23.8, so it's a 0.0762 ohm, and AC resistance AC equal to KC into average into RDC, so it comes 1.3 into 0.0762, that becomes 0.099 ohm. Now coming to numerical problem 2, a 500 kVA 33 kV 50 Hz 600 RPM 3-phase silent pole alternator has 180 turns per phase. Estimate the length of air gap if the average flux density is 0.54 Weber per meter square. The ratio of pole arc to pole pitch ratio is 0.65, the short circuit ratio is 1.2, and the contraction factor is 1.15, and the winding factor is 0.955. The MF required for gap is 80% of the no load MF, and the winding factor is 0.955. So now, as a solution here, synchronous speed is NS equal to 600 by 60, that is 10 RPS. Poles are 2 into 50 by 10, that 10. And current in per phase IPH is 500 into 1000 divided by under root 3 into 33, that's 87.7. And the armature MF is 80 equal to 2.787.7 into 180 into 0.95 divided by 100, that is 10.62 ampere. The no load MF per pole 80 FL 80 F0 equal to SCR into ATA equal to 1 into 4062, that is 4875 ampere, and field force factor is gap equal to psi equal to 0.566. So maximum flux density in air gap is B is equal to B average upon KF, that is 0.54 divided by 0.66, that is 818 Weber per meter square. The MF for air gap is 800,000 Bg kg Lg, that is 0.8080 F, that is 0.84875. Length of air gap is Lg equal to, putting a value this all in this relation comes 5.2 millimeter. So, well, coming to numerical problem 3, 1250 kVA, 3 phase 50 Hz, 330 volt, 300 RPM synchronous generator with the consenting winding has the following design data: specific magnetic loading B average 0.58 Weber per meter square, specific electric loading AC equal to 33,000 ampere per meter, gap length 5.5 millimeter, field turns per pole 60, short circuit ratio 1.2, and the effective gap area is 0.6 times the actual data. Peripheral speed 30 meter per second. Find the stator core length, stator bore, turns per phase, MF for air gap, armature MF per pole, and field current from no load to rated. So synchronous speed NS equal to 5 RPS, number of poles P equal to 20, and output coefficient C0, putting the value it comes 201. Then D square L equal to Q upon C0 NS comes 1.245 meter cube, and from D from peripheral speed PA upon pi n, so it comes 1.9, and L from output equation relation it comes 0.345 meter. And now area per pole pi into pi d into keeping a relation, it comes like 0.103 meter square. Flux per pole, putting a value in relation, it comes 59.7 10 power minus 3 Weber, and volt per phase EPH 3300 by root 3 1910 volt. Now turn per phase is from induced EMF formula per phase, E divided by 4 F pi into typically kW, that's 150. Current per phase is your kVA into root 3 into V, that comes 219 ampere. Armature per pole, putting a value in the relation of 2.7 IPH into kW divided by your number of pole, that's come 4240. Effective area per pole, putting a psi into this 0.6 into this comes 61.8 into 10 power minus 3 meter square. Now effective gap density kg into Bg, the flux per pole into area per pole, putting a value comes 0.966 meter square. MF for air gap is 800,000 Bg BGLG, that comes 42.5 ampere, and field MF per no load ATV0 is 1 SCR into ACTV, that comes 51,000, and field current is your field MF divided by the number, that comes 85 ampere. Now coming to numerical problem 4, a 2500 kVA 225 RPM 3 phase 60 Hz 2400 volt star connector 7 pole alternator has the following data: stator bore diameter 2.5 meter, core length 0.44 meter, stator per pole arc per phase 3, conductor per slot 4, circuit per phase 2, leakage factor 1.2, winding factor 0.95. So flux density in pole core is 1.5 Weber per meter square. The winding depth is 30 mm, and the ratio of full load MF to armature MF is 2. Field winding space factor is 0.84. The field winding dissipates 1800 watt per meter square of the inner outer surface without temperature rise exceeding permissible limit. Leave 30 mm for insulation, ping, and height of pole 2 along with the height of pole. Find the flux per pole, length of and width of the pole, winding height, and the pole height. Now calculating synchronous speed in RPM divided by 60, so it's 3.75 RPM. Number of poles P equal to 2 into 60 by 3. So it comes like 32. Total number of slots 3 into 32 into 3.5, that's 336. Total number of conductors 336 into 4 1344. Turns per phase is equal to total turns by 6, so it comes total conductor by 6, so that's 224. And turns are connected to parallel path. So voltage is V equal to PH equal to 2400 by root 3 1390, and from relation EPH equal to 4.44 TPA divided by A into FKW. So flux per pole from this comes 49 10 power minus 3 Weber, and flux power in pole body 5P equal to K factor into flux pole, putting value to come 58.8 into 10 power minus 3. Area of the pole body AP is 5P on BP, so putting value to come 39.2 into 10 power minus 3 meter square, and length of the pole body LP equal to length of core is 0.44 meter, and width of the pole body BP equal to, just putting a 5B in the, so it comes 0.89 meter. The current in each phase from kV relation, it comes like 600 ampere. Current in each conductor, IZ equal to 600 by 2, that's a 300 ampere. And since there are two circuit per phase, armature power 88.7 IPH TPH into kW divided by P, that's come 575370, and field MF at full load 8 equal to 2 into 88, that's a 1740 ampere. And MF per meter height of the winding 10 to power 4 under root SF DF QF, bring a value, it comes 67,300 ampere. Now the height of the field winding HF equal to this divided, so it comes 0.16 meter, and height of the pole height equal to build height, so it comes 0.19 meter. Now coming to numerical problem 5, a 1250 kVA 3-phase 6600 volt cell and pole alternator has the following data: air gap diameter equal to 1.6 meter, length of the core is 0.5 meter, number of poles 20, armature ampere to 28,000, ratio of polar to pole pitch 0.68, and stator slot pitch 28 mm, and density in damper watts 3 ampere per millimeter square, and design suitable damper winding for the machine. So solution is pole pitch equal to tau equal to pi air gap diameter to a number of poles, putting a value, it comes 0.251 meter, and total area of damper bars AD equal to 0.2 AC tau divided by BD, so it comes like 470, putting value 473 millimeter square. Now the pitch of the damper bar is taken 0.8 times the stator pole pitch, so number of bars per pole is N equal to pole arc divided by 0.8 into 8 stator slot pitch, so it comes 7.6, so which is rounded to 8. And area of the bar is 8 equal to total area number of bars, so 473 by 8, that's 59 millimeter square. Now diameter of each bar D equal to under root AD upon 5 by 4, putting value 8.7 millimeter, and length of the bar equal to 1.1 into L, that comes into 0.5 meter. Now numerical problem 6, a 588 MVA 2200 volt 50 hertz 2 pole 3 phase star connected direct water cooled generator has the stator bore of 1.3 meter and stator core length of 0.6 meter. The stator winding has a 2 conductor per slot, and there are 2 circuits per phase. Calculate the number of stator slot and B, the average flux density in their gap. The specific electric loading 200,000 ampere per conductor per meter, and assume a winding factor of 0.92. So speed is NS equal to 50 RPS. Voltage per phase is 22 divided by root 22,000 by root 3, that's a 12,750 volt, and current phase is the kVA divided under root 2 into V, so it comes typically 15,400. Current each conductor is I is equal to, because of 2 parallel path, I upon 2 parallel path 7,700 ampere. Now specific electric AC equal to IS Z by pi D, putting value from here, the Z comes, putting value 106. The total conductor has to be modified so that suitable number of slots can be used. So one should choose this number in such a way that the number of poles per turn per phase and the number of slots per pole are in integer. So for 3-phase machines, the turn per phase is TPH equal to Z upon 6, it's 18, and actual number of conductor Z is in 6, 18, 108. Number of slot S equal to conductor per slot come 54, and the number of slot equals to 50 are suitable for winding. So for a winding with 2 circuit per phase, EPH equal to 4.44 FP TPH kW by 2. The flux per pole from this relation comes 6.92 Weber, and pole pitch tau equal to pi D on number of poles, so comes 2.04 meter, and average flux density B average equal to 5 upon tau L, so it comes, putting a value 0.565 Weber per meter square. Now these are the references from which this lecture is prepared, so you can go through, and thank you very much.